Welcome to this explainer. It really does feel a bit like witchcraft when you type a prompt and instantly get a photorealistic movie scene, doesn't it? But today we're going to pull back the curtain and explore the mathematical magic behind AI video generation. Behind the screen, it's all math, massive amounts of data, and just brilliant engineering. Let's find out how this actually works under the hood and map out the fiercely competitive 2026 production landscape.
Here's a quick roadmap of what we're covering today. First, the AI video problem. Second, the solution, specifically the spatiotemporal DIT. Third, fixing the flicker and pitfalls. Fourth, the 2026 landscape. And fifth, the memory bottleneck.
Okay, let's jump right in. To immediately put the sheer scale of this challenge into perspective, generating a 3D video requires 10 to 100 times more computing power than generating a 2D image. The underlying theory between image and video generation is actually pretty similar, but the execution is a totally different beast. Let's look at why.
Part 1. The AI video problem. Picture just a tiny 10-second video clip at 1080p resolution, running at a standard cinematic 24 frames per second. That's 240 individual frames. If you calculate the raw pixels there, you're looking at roughly 1.5 gigabytes of raw pixel data just for those short 10 seconds. Doing traditional pixel space diffusion, where an AI tries to denoise every single pixel one by one, is literally impossible. The computer would just choke on it.
So to overcome this impossible data size, production models absolutely have to rely on four crucial components. First, spatiotemporal compression. Basically, we need an encoder that compresses whole videos, not just individual frames. Second, flawless temporal coherence, meaning lighting and objects actually stay consistent over time. Third, a massive compute budget. Remember that 10 to 100x multiplier we just talked about? And fourth, flexible conditioning, which is just the ability to tell the AI what to make using text, a starting image, or even audio.
Which brings us to Section 2, the solution, spatiotemporal DIT.
The very first trick up our sleeve here is compression. We use a tool called a 3D variational autoencoder, which acts kind of like a super smart zip file, to break down the massive video into what we call patches. So instead of billions of pixels, the AI just looks at fixed-size 3D blocks of data. This takes our unwieldy 1.5 gigabyte 10-second clip and shrinks it all the way down into 20,000 to 100,000 manageable 3D blocks. This right here is exactly what makes the math possible.
And here is where it gets really clever with how we save computing power. Factorized attention. Look, if the AI tried to process all that 3D data, every patch across space and time simultaneously, it would be 16 to 100 times more expensive. Instead, factorized attention looks at space and time separately. It checks the spatial layout within a frame first, and then it checks the temporal changes across the frames. It's a genius shortcut to keep from running out of memory.
If you were going to build this yourself, say in Python, you'd basically follow a clear four-step assembly line. Step 1, patchifying the video into those blocks. Step 2, pinning position embeddings to the frames so the AI actually knows when and where each block belongs. Step 3, denoising the whole sequence jointly rather than independently. And finally, Step 4, testing the frame-to-frame deltas to make sure everything flows smoothly.
Now, what's actually super interesting about this is that the secret weapon isn't just the architecture. Data captioning matters even more than size. Models like OpenAI's Sora achieved their massive breakthrough by training on highly detailed AI-generated recaptions. They essentially used an LLM to relabel all their training clips with incredibly dense prompts, averaging about 200 tokens per clip. This taught the video model exactly how to understand really complex text requests.
Let's move to Section 3, fixing the flicker and pitfalls. So why did early AI videos look like some kind of glitchy fever dream? Well, the crucial point is right here. If you run image diffusion on each frame independently, the AI is basically shuffling random photos that just happen to look somewhat similar. The result? Severe flickering artifacts. But if you couple the frames together through shared noise and joint sequence sampling, it flows perfectly, kind of like a beautifully drawn flipbook. Then there's another massive hurdle called physics drift. You know when a video goes past 10 seconds and suddenly objects start melting or gravity just stops making sense? That's physics drift. It's those subtle inconsistencies that accumulate over time. To patch this up, engineers use techniques like sliding window generation and keyframe anchoring. They're essentially pinning specific frames to lock in the video's core arc, which keeps the AI's internal physics engine from going totally off the rails.
All right, zooming way back out, Section 4, the 2026 landscape.
As this chart outlines, the field has absolutely exploded. You have proprietary, closed models like Google's VO2, which leads the pack in raw 4K quality and physics simulation. You got Sora Turbo, running 5 times faster than the original. But then, look at the open-weight models like Alibaba's WAN 2.2. They are aggressively closing the gap. It proves you don't need to be locked into a tech giant's ecosystem to get stunning results. And in fact, WAN 2.2 is powering most open-source workflows today.
But the real takeaway here is how you actually apply this stuff in the real world based on your needs. If you want precise camera control for a cinematic shot, Runway Gen 3 is your best bet. Need character consistency across multiple clips? Go with Pika 2.0 or Kling 2.1. If you want to run quick fine-tunes on your own hardware, WAN 2.2 combined with Allura, which is essentially a small custom style patch, is absolutely perfect. And for built-in lip syncing and native audio, VAEO 3 is the clear winner.
Let's wrap things up with Section 5, the memory bottleneck.
It turns out the true constraint in production isn't actually just pure math computation or sheer flops. It's memory bandwidth. Remember those compressed patches we talked about earlier? Well, even compressed, you are forcing up to 3 gigabytes of data through the GPU's high bandwidth memory, or HBM, for every single step of generation. If a video takes 30 steps to render, that memory bus is getting completely hammered. So to stop these systems from just totally choking on all that data, production engineers use 3 pretty hardcore tricks. First, tensor parallelism, which splits the massive workload across multiple high-end H100 GPUs. Second, continuous frame batching, so they actually start rendering frame 2 while frame 1 is still returning, to save time. And third, they utilize a clip-level prefill cache. This acts just like an LLM's memory. It computes the first frame once and reuses it, so they don't have to recalculate the starting point over and over again.
All this brilliant engineering has led to a pretty staggering reality. Knowing that the cost of generating AI video has dropped an astonishing 20 times in just 2 years, between 2024 and 2026, this tech is becoming accessible to everyone. So I'll leave you with this to ponder. What happens to our media, our entertainment, and our very perception of reality when every single person holds a flawless, real-time world simulator right in their pocket? Think about it. Thanks for joining me on this explainer, and keep learning.